for you guys to do like other work on. I actually made a note to myself, though. I think instead of that, I'm going to put one extra blank page in between each problem, because I write down stuff that almost takes up the whole, and then you need a blank space in there to do your work first. So I think I'm going to change that for next time. Yeah, I mean, there's a lot of good stuff in here that sometimes it ends up being I pick and choose what I want to.
Yeah, I was looking at it too. It was interesting.
And I was wondering, because you do things with least common multiples, greatest common factors. Some of the stuff I'll probably end up looking at in PCK2 first, but PCK2 is a little bit different. But if I can maybe spend a couple days doing some of that stuff, we can work at it that way. So. Well, but today I do want to make sure that we can derive the quadratic formula, possibly use an alternative to the quadratic formula, and then explain why a to the 0. That's hopefully going to end up being an easy explanation there. So, this is number 14, and everybody needs to know how to derive the quadratic formula. I'm going to derive it the most common way. I think the easiest and the most intuitive way. And I guess now thinking about thinking about a lesson that I observed the other day, yesterday I guess it was. I'm thinking, I don't know if you really have to do the order that I'm going to do, but I'll show you what I mean here. So the first thing I want you to make sure you get about the quadratic formula is this: completing the square. So I don't know if you remember that technique. If I said completing the square off the top of your head, do you remember that? We actually even talked about it in history of math, where it had me. But how to complete the square? Is that? I mean, I'll review it there real quickly. But completing the square on the general quadratic, ax squared plus bx plus c equals 0, derives the quadratic formula. Now, just a very quick review. Everybody in here, I hope, would agree that trinomial is a perfect square trinomial. We recognize it because of what as a perfect square trinomial? What makes it a perfect square trinomial? Go ahead, Jess first. What were you going to say?
I was going to say that 3 times 3 equals 9, and then 3 plus 3 equals 6.
Okay, so 3 times 3 is 9, so that's a square. And you said 3 plus 3, or 3 plus 3, another way of saying that is 2 times 3, right?
Yeah.
3, 2 times.
Yeah.
All right, now the reason I want us to look to observe it that way is because of what I'm about to do with completing square. Because if I were to leave you hanging and say that obviously is just it's a binomial, it's not a trinomial at all, but if I said I wanted you to complete the square, okay, which means to make that, now I'm going to say make a trinomial, so I'm going to pretend it's trinomial. Make a trinomial that is a perfect square. So I guess what I mean there is, that's why it's perfect square, because you can write it as something square. Just like 36 is perfect square because it's 6 squares, right? We've got that before. So I say complete the square on this partial trinomial, okay? And what would you do? Well, you know the answer is 9, but how do you do it? Half that, right? That's why you said, I mean, you say double that, and then square. So you take half of it, and then square it, okay? Which gives you 9. Now, I like to also look at things like this and say, that's a trinomial. Complete the square on it. Make it a perfect square. Well, you got that 8, okay? Now, how do I know that? Well, because half of that squared is 9, and I already have 1 there, whatever. Somehow I have to make that a perfect square. So, Now, that only works though. That only works when the coefficient is 1. If, think about this. Right, so if that is 3, if I say it's 2, obviously that's not a perfect square trinomial anymore, but I guess if I said that was 12, is that going to do the right thing? And that's 18, it's not a perfect square trinomial. Like I'm not going to be able to write that as, well, it's partly because of that 2x, right? You know, 2x, right? But I could factor out a 2, then rewrite that like this, and then, I mean, the whole thing's not a perfect square trinomial still, I get that, but you know, at least I can rewrite part of it, you know, in there as a perfect square trinomial. Now, if, and I hadn't really thought about this before, but let's say, let's do that, and you know, this leads to the quick way of squaring something, right? Is, you know, if I know the thing I'm going to get is a perfect square trinomial, 4x squared, and then multiply those together 6x and double it. So 12x, and then square that, 9, right? So now though, if I looked at that, if I started out with 4x squared plus 12x, is there a way that I can find the thing that I would add to get a perfect square trinomial out of that? So I know it's 9, right? Taking half, that's obviously 6. And then,
Then 2 again.
right, divide by 2 again.
But I don't know if that would hold.
Right, now is it 2 because 2 is half of that? Or is it 2 because it's 2 again? Well, let's check it. So what I mean is, let's say I have, let's do it with 3x plus 4, right? 3x plus 4 is 9x squared, I'm not really taking time to do this. So 12x and 24 then, right? So plus 24x, and then 16.
I think you divide by.
So it's, yeah, because this is, half of that is 12, you divide by the square root of that.
Yeah.
Okay, because I figured it had something to do with the square root just because that's squared. So if I divide that in half, it's 12. And then divide by the square root of that is 3, which is, wait, no, hold on. 12 divided by 3 is 4, and then square that is 16. That, you know, I'd have to prove it, but intuitively, that makes sense, right? I mean, we could probably prove that, I'm not going to right now. The point, though, is, what we do is we complete the square on the general quadratic equation, which we all ought to be able to do off the top of our heads, because we know algebraic manipulation, and we understand that this is just how it's done. We complete the square on it. Which is why when when my student teacher yesterday, and we were talking about his lesson the day before, and he said, I'm going to teach, well, he was going to teach the quadratic formula. And then he made a comment that, well, I think I'm going to do something that the book doesn't do, whatever. I'm going to do completing the square first. And my comment was, I don't know how you wouldn't, or why you wouldn't do completing the square before you do the quadratic formula, because how else do you get the quadratic formula? Well, there is another way. Just give it to them, right? And you say, who cares where it came from? You know, and I'd probably say, 90-some% of teachers don't show their students how to get the quadratic formula anymore, because they'll say something like, well, they don't have to know that for the test. Stupid answer, or stupid reason. Or my students aren't going to understand it. Hate that, reason at all, because all you're saying there is your students are dumb, and it's not difficult to understand. When I think I said that before, what that really probably means is I don't really know how to do it, myself. So here's what we do. We start with ax squared plus bx plus c equals 0. And the first thing to realize is, without some fancy crap over there like I did for the last couple, the coefficient of x squared has to be 1. So that's my first thing. Completing the square, we like to say, completing the square only works if your coefficient is 1. Well, I guess without doing this, right? Let's see if this, watch. Let's see if this works. If I complete the square on this, plus something. let's use our trick, right? But it's not perfect, right? So what I mean is half of that is 6. So 6.
Oh, God.
And then I'm gonna divide that by square root of 2, but you might say, well, that's kind of, I don't divide by square root of 2 there, but I'm squaring, right? I'm squaring, and that's fine, because that means that's gonna be 2. So I get 36 over 2, 15. And that's what it was, right? Well, wait a second, was that right?
Yeah. Yes.
Oh, but wait a second though. That gave me the perfect square after I factored 2 out. This is still not a perfect square because of that. Except for, right? We go to modern algebra now, right? And we say, it is math, right? It is. It's a perfect over the set of irrationals, which usually we only factor over integers. But we could do it that way, and that would work, right? This squared is that. This times 2 though.
No, it was
What
18. It was originally x squared plus 6x plus 9. So the 18's right.
Well, right. What I'm saying
Yeah,
is this right here. I'm not going to be able to write as something squared. Oh, 3 anyway. Yeah, sorry. Yeah, that's it.
Okay.
That's it. That's right. That's my perfect square. Stupid looking. But what I mean is, that threw me off when I multiplied, because I accidentally put a 3 down from the old problem. Because this squared is 2x squared. Multiply those together, 18 times 2 is 36. The square root 6, right? And then double that, 12x. And then that squared is that. So it does always work, but that's too weird for me when I'm okay with using fractions. What I mean is, so here's how the process goes. First step is get this to be a 1. Divide by a. So what's it look like? X squared plus b over ax plus c over a equals 0. Right? Divided both sides by a. It just happens to be this is 0 still. My process of completing the square says this. Get this guy over to the other side so I can just complete the square on this. And this is just a constant over there. Because remember why we complete the square? We complete the square so when my left side, remember this is all going to hook together from the last 2 questions. When my left side looks like that and my right side looks like that, I can use the, not square root both sides, I'm using the square root property, right? And I'm saying, if x plus 3 squared equals 9, then x plus 3 equals what? Careful. I'm going to get right, because I'm using the square root principle. And that's where it says that going from here to here just says that the square root of that equals the plus or minus square root of that. Now, if I'm going to do absolute value, that's fine. But that's how I get my 2 answers using the quadratic formula. But that's why I complete the square. That way, this side's a perfect square, and I can get rid of my x, right? Because here's the problem. If you just say x squared plus 6x equals 9, you can't isolate x. You can't take the square root of, like you could with x squared equals 16. You can't do that. All your techniques break down. But if I make it a perfect square, then I can, if you want to look at it that way, whatever. But now I can do it. So, the key to doing that, though, is get c over a to the other side. And now, complete the square. I mean, can you tell me that you've never seen this done? And anybody ever, I know you've used the quadratic formula. Have you seen it derived, though? Never seen it derived? Because unfortunately, and probably not. I mean, honestly, probably not. But we continue here, and we say, okay, well, what do I do to this? I have to add something, which is going to be half of that squared. And I'm going to do it to the other side as well. Half of that is b over 2a, and squared is b squared over 4a squared. plus b squared over 4a squared.
What about the x? Oh, never mind.
No, it's just half the coefficient squared. Now, here's what you just did, right? You made this a perfect square. With first term, x. Second term, don't think about it too much. It's the square root of that or the half of that, right? It's b over 2a, right? b over 2a. What's that right side equal to? Well, you start to see the quadratic formula starting to fall out, right? So 4a squared, I'm going to multiply both the numerator and denominator by 4a to make them have a common denominator. And then since this is first, I'm going to put that second. So it's going to be b squared minus 4ac all over the 4a squared. Now, I convinced a teacher at Williamsport 3 or 4 years ago to let me, because the student teacher again was like, oh, this is my inclusion class, and they're not going to understand how to do that. After I had stayed and watched him teach the quadratic formula by just giving it to them, I said, why don't you derive it? And he was like, oh, my students couldn't handle that. And I said, let me stay. And I knew the co-op well too. And I was like, let me stay and do it. And they're like, okay. And the kids were eating it up. They were like, finally, somebody's telling me where the crap comes from. Instead of just giving it to me. So it's not like they don't want this. All right, now do you see? Now what I did though is this: I didn't force them, because at a different level in class I'm going to do different things with, and I didn't force them to do all the algebra. They just followed me, in the algebra. But I just wanted them to see it and appreciate where it came from anyway. Now this is the beauty in this completing the square method. I get this squared equals that, and I use the square root principle. And I say what that means is then that x plus b over 2a equals plus or minus the square root of b squared minus 4ac all over 4a squared. And then of course, I can isolate x now, right? Isolate x by then saying x equals, so I'll put the b over 2a over to the right hand side, and it's the opposite of b over 2a, plus or minus, keep the square root of b squared minus 4ac, but then of course the square root of 4a squared is 2a, right?
Yeah.
Does it look familiar? So x equals the opposite of b plus or minus square root of b squared minus 4ac all over 2a. And finally, the quadratic formula came from someplace instead of out your rear end. And it's sad that that's the first time you've ever seen the quadratic formula actually derived.
I think Jim did once. But
Well, if you had Jim for like a pre-calc class or something like that, I'm
yeah,
sure it
it's-
did.
yeah,
Okay,
that's what I had.
But again, if you started out here in calculus, and this is the danger, I guess, in starting here in calculus, so many teachers in high school aren't doing, things, they're just giving students formulas and that don't know where it's coming from, and calculus is justice. Well, anyway, so I would say this though, and I want to show you one. I have two other ways. Just maybe you can process this with me. I'm just going to do one, and I'll just say there are other ways. There are other ways to get the quadratic formula. Just want to make sure I get to some other things here. Now, so this one right here. You start with ax squared plus bx plus c equals 0. And I guess if certainly completing the square is the most common and the more traditional way of doing it, and it's the way that at least allows you to say, I don't really know what's going to happen here, but let's just use this other method of completing the square on this general form, and see what happens. Then out pops a formula. These other ways are fine ways to derive it, but they also appear to me to be ways that you already have to know the end. You know, and not that those aren't good, but in a way sometimes they're a little deceptive. You know, if you know where you're going to go. So I certainly stay with the claim that doing it through the quadratic formula is the best way to do it. Okay, so or doing it through completing the square. Sorry. So this way looks. So I guess my point is when the kid says, "Well, I don't have to complete the square in order to do the quadratic formula first," I might say, "Okay, but you're still not deriving it, you know, anyway. So, you know, what are you doing?" Well, anyway, so this formula looks like this: multiply both sides by 4a. And you say, multiply that side too, it's still obviously going to be 0. And you might say, well, where'd you get the 4a? Well, it's because I know where I'm going. Okay? So, when I do that, I get 4a squared x squared plus 4abx plus 4ac equals 0. And really I need my 4 there because I need this 4ac, I guess, right? B squared minus 4ac. Okay, now I will do this though. So, you know, because what can I do? I can get away with saying, you can multiply, you know, as long as you multiply both sides by the same number, right? And I guess you should probably be a little careful there and say, well, you can multiply both sides of an equation and get by the same number and get an equivalent equation, but you can't multiply them both by a or by 0. But that's okay. A would never be 0 because then you don't have a quadratic equation, right? Okay, so we're okay there. So now, I haven't done anything that I need to complete the square of it. That's my basic point. So I say 4a squared x plus 4abx, and I'm going to move that 4ac over to the other side, make negative 4ac. Now, so you might put a little note to yourself that says multiply by 4a.
Is it 4a squared x squared?
This stuff. A squared x squared again, sorry. Now what I'm going to do is this. Now I'm going to add b squared to both sides. Where'd b squared come from? Yanked it right out. Okay? Well, let me tell you where b squared came from, right? Let's think about this. Half the coefficient, right? You know, but right now, but I'm not really completing the square. I guess technically I could probably say the same thing over there and say, don't really complete the square, just add this to it. But then where'd you get this? Okay, so but now we actually know this, right? Take half of the coefficient of x, that'd be 2ab. And if I divided it by the square root of 4a squared, that's dividing by 2a, and I'm left with b, then square it, right? B squared. So that makes sense, but no, I'm not completing the square. Except for the fact that where'd you get that? You completed the square. So I don't think that that's a very sound argument. But anyway, so what's that give me then? It gives me 4a squared x squared plus 4abx plus b squared equals, I'll say just b squared minus 4ac. Right? Now though, even though you haven't used the process of completing the square, we recognize this as a perfect square trinomial. 2a plus b squared. So you might get away with saying, in this way, I don't have to use completing the square, but you're a liar.
I feel like you assume a lot with this.
Right, you do. You assume where you're going because, well, why don't you multiply it by 8a? Well, 8a you might be able to do because 8's a factor of 4. So let's say, why don't you multiply by 3a? Because you do, well, you can. You're just not going to get to the b squared, right? But you might get to another formula. I'll have to check that out. You might get to another formula. Like, what if you did that and then you got another formula? We'll see. So anyway, b squared minus 4ac. Then that means what? That 2a plus b equals plus or minus the square root of b squared minus 4ac. Oh wait, where's x? Where's x?
Yeah, you didn't.
I forgot x here, right? That's x. There's an x there. Because then solve the thing for x. And what do you get? You get 2ax. Well, actually, can I do this? I just solve for x. So b's going over, negative b plus minus square root of b squared minus 4ac. And then you're dividing by 2a, and there it is. Now, the last thing about this here is, now watch how I'm going to say this. I'm going to put it all in capital letters here. The quadratic formula is not, and then lowercase, the only quadratic formula. So that might come as a shock to most teachers. The quadratic formula, when I say that, I mean x equal opposite of b plus or minus square root of b squared minus 4ac all over 2a. You know, I mean that. That's the quadratic formula. Is not the only quadratic, little lowercase, the quadratic formula. It's not the only formula used. Well, I gave you x equal 2c over opposite of b plus or minus square root of b squared minus 4ac. So use that to solve, and what was the question? 2x squared plus x minus 6 equals 0. Now in the interest of time, I'm not going to solve that using the quadratic formula. I'm going to assume that you could do that. I will tell you that the answers, using that method, would be negative 2 3/2. Okay? But I'm going to use it, I'm going to use this new formula. So x equals 2c. I mean, we're okay, right, with saying a is that, b is 1, c is that. So c is negative. So can I say, I'll just put negative 12 up there on the formula? I'm not going to do, I'll put everything in there. The opposite of b would be negative 1. Plus or minus, and then square root of b squared. So it would be 1 minus 4 times a is 2 times c is negative 6. So it's negative 12 over negative 1 plus or minus square root of, that's 20, 48, 49, right? 49, which is negative 12 over negative 1 plus or minus 7, which is negative 12 over negative 8, or negative 12 over positive 6, which is equal to positive 12/8, which is 3/2, or negative 2.
Oh, that was 2, okay.
Oh yeah, wait, what? Oh, 2 comma.
2 comma 3. I thought you
Yeah.
said 2 3/2.
Oh no,
2
negative 2
and
comma
3/2.
3/2. Yeah. Yeah, and actually, it's
That's
funny
why
that
I was like-
funny that you catch the and that, because this is something I've always struggled with in teaching, is you have to be careful. Like, should we say that x equals negative 2 and 3/2, or should we say negative 2 or 3/2? It actually all depends on what you're really saying, I guess. So what I mean is this: it certainly can't be and in the sense that you can't
At
plug
the
in
same
both of them
time.
at the same time,
Yeah.
right? But if we say that the solution set, which is really what we're really saying, I mean, I know this is a lost art, but when you solve 2x plus 3 equals 5, and we get x equals 1, we say x equals 1. Back when I first started teaching before, our textbooks wanted us to write the answers like this, though, because the answers are the set of numbers. We're so focused on the one number that can go in, but it's really the set of numbers that makes the equation true. And the set is the set that contains 1. The set is the set that contains -2 and, right, 3 halves. So it really all matters, are you saying it's the set, -2 and 3 halves, or is it -2, or you can put in 3 halves, you know? So it really all depends on what, you know, context you are thinking of. But the point here is, I get the same answers. Now, I'm not gonna do this because in the interest of time, but it is interesting to see that I could actually derive that formula doing the same thing using completing the square. So it's always completing the square no matter how you look at it, I guess. Using completing the square, if you did this. Now, in order, it is kind of strange because what I'm going to do is I'm going to divide by x squared. Okay, you know how you divide by a first? This time I'm actually going to divide by x squared. Now that does imply then that you're assuming that x isn't 0. And of course, x could be 0 because if c was 0, you know, this actually brings up the point very well that if c was 0,
You can't use this.
so, well, no, you can use it, but if c was 0, one of your answers is 0 because the numerator is 0, right? So anytime you have 2x squared plus x equals 0, one of your answers is 0, but you know that because you can factor out an x. And of course that means that one of the answers is 0. So this actually is nice in the sense that it actually tells you when one of the answers is 0. But in order to derive it, I have to divide by x squared, which means I'm going to assume that x isn't 0 then. So that may seem a little strange, but anyway, if you do that, if you divide by x squared and then you multiply by c, you actually will get, over here you'll be solving for 1 over x. You won't be solving for x, you'll be solving for 1 over x. And 1 over x is this, so then x is, you know, invert them, and there it is. So it's a little weird though that you actually see that x equals opposite of b plus minus squared b squared minus 4ac all over 2a from the original formula, right? 1 over x though actually equals opposite of b plus minus squared b squared minus 4ac all over 2c. That seems weird. It's just the reciprocal of it means to put that in there. There's a little bit more investigating probably that you could take that and, you know, and further your understanding, but that's where we're stopping there. Yeah, so I find that kind of interesting that x, the only difference between x and 1 over x is how it is c. But I guess if you, I don't know, look at it this way here, when x does equal, I'll do 3 halves then. If x is 3 halves, then 1 over x is 2/3, right? Well, the 2 certainly had something to do with over 2a, right? So it had something to do with a. I guess the point here is that the x, well, 1 over, I guess it's 1 over x, right? So that means that if it's x, am I saying that right though? If it's x, that has, that, yeah, because it's just x, that has to do with that. And there's nothing, 1 over x, the denominator does not have anything to do with a. But it's 1 over x anyway, so yeah, I don't know if I'm saying that. I'm not saying that in any I'm not sure if I'm saying that in any understandable way or not, but when it's x, because the formula is over 2a, and certainly that has something to do with, it's not necessarily 2a because it could be simplified, but it has something to do with a. When you say here, what are we saying though with that? I guess we don't know. I'd have to further investigate that to see what.
Did you set the 2 equations equal to each other?
Well, yeah, and that's I've done that in the past. The 2 formulas, you mean?
Yeah.
Yeah, and what are you looking for when you do that? When you say that, what do you mean? Like what?
You set 2c over negative b plus or minus the square root, that one, and then literally just the other one.
Yeah, and what would you be looking for? You would just be looking for.
Well, you could see the relationship between the a and the c then, the 2 things that are different in the formula.
Right, so if they are though, if they are equal, if we're saying that negative b plus or minus square root of b squared minus 4ac, I know before when I played with this, I've done this, is equal to, what is it, 2c? if you do that, I mean, I'm pretty sure you end up with just 0 equals 0. It doesn't show anything.
Yeah.
Is that what you mean? Because think about it. These two multiplied together give me 4AC. And then these two multiplied together, yeah, you get a little of the plus minus thing happening here.
B squared.
In order to multiply them together, well,
Oh, yeah,
if you think of conjugates
We
there,
have 2.
if you think of conjugates, you end up with b squared, and then these. Actually, I don't even think you can make conjugates because no, you can't do conjugates because that means this, and then this times a plus, and this times a minus cancel, and then this times this is going to give you, but it's going to be one's a positive, one's a negative, so it'll be a negative b squared minus 4ac. Well, that's where b squared minus b squared is going, and then negative negative. So that's 4ac equals 4ac. Okay, that tells you 4ac equals 4ac. If you, I'm trying to think of the reason why one has to be positive, one has to be negative, because if you do both positive, then you end up with b squared, and then you're going to have this times this, basically this times this double, so minus 2b times the square root of b squared minus 4ac. But then you're going to have plus b squared minus 4ac. Well, then those go, and what do you have here though? Yeah, wait, oops, I said it right. Yeah, those go. But then you have your negative. Oh, that's positive.
Negative 2b
No, that's not right. So, but then you have the negative 2b.
is equal to 0.
Yeah, so I'm not sure. It doesn't. I know I ran into trouble with that before. I think last year was the first time we looked at this problem here. I'm not sure why to make it work. One has to be positive, one has to be negative, because that doesn't seem fair. You know, like why wouldn't you be able to use? Why do you have to set the one? Because that's not setting the same one. Oh, you know what? But that actually is. Because, right, when I do, it is strange. You have to go through the process here. It is strange though that the first one here is the second one here. And the first one here is the second one here. And it has something to do with that. But I'm going to stop right there because that's going to take us longer than we have to.
Sorry for going off track.
No, that's not really off track.
I mean,
it
yeah,
is.
on that.
Yeah.
Cool.
Just because I think number 15, I did want to say a few things about number 15. I mean, that right there could, you could write a paper on this, I think. You know, you could look at it a little bit deeper and probably write a good publishable paper on, you know, using that and how to make them equal and why and stuff like that. I think it would make for a really good paper. Anyway, number 15 though, the a to the 0 equals 1. So the first thing I want to make sure we run into that is a pattern can be a powerful convincer of arguments. So what I mean is, the first pattern I look at goes very similar to our product of two negatives equals a negative. You know, it's not a definition, and I'll say that later on in one of my comments. Please don't say, it's just defined to be 1. That's a terrible answer. It probably shows your ignorance of not understanding the thing that you're teaching. And so we don't want to do that. So 3 to the 4th, there are some things certainly I can't explain well, but those should be few and far between that you just use, especially this basic stuff. So 3 to the 4th equals 81, and then 3 to the 3rd equals 27, and 3 to the 2nd equals 9, and 3 to the 1st equals 3. Those are all things that we can say, well, yeah, sure, 3 times 3 times 3 times 3, 3 times 3 times 3, 3 times 3, 3. And then just look at the pattern. What's the relationship between 81 and 27? Well, certainly you're dividing by 3 because it's one less factor of 3. And then this right here is dividing by 3, and this in here is dividing by 3. So the next logical place in the pattern is 3 to the 0. Well, keep the pattern. I want math to be consistent, right? I want it to make sense. So if I divide by 3, well, it's 1, right? you use the same argument to say, what's 3 to the negative 1 then? It's beyond this problem, but still you divide by 3. That's 1 over 3. Yeah.
I think a very important lesson to take from this is to go back and explain to your students what the base and the exponent mean in the form of the power.
Right. And part of that, and we were talking about this after class on Tuesday, is understand this, and this is a pretty big leap. What I mean is, from an understanding of exponents, which is use that number, the base, that many times as a factor, right? From that perspective, positive exponents make sense. The point at some point in your textbook is we want to extend our understanding of exponents from a positive number to 0 and negative, and eventually fractions. And there's another part in here that says, well then what does this mean? What does 25 to the 1/2 mean? Well, we know it's the square root of 25, which is 5. But why on earth is it 5? Well, it's 5 because if you square that and use your exponent rules, you get 25. If you square that, you get 25. So the square root of that, well, the square root of 25, must be, that means the square root of 25 being 5, that means that this must represent the square root of 25. So there are good logical arguments for that when we just want to extend. But the point is, if I extend this to say, 3 uses the factor 4 times, 3 uses the factor 3 times, 3 uses the factor 2 times, 3 uses the factor 1 time, I'm okay. 3 uses the factor 0 times. Doesn't make any sense, right? Doesn't make any sense. 3 uses the factor, so don't put 3 down at all, but do some multiplication. What? Doesn't make any sense. So I have to look at it from another perspective. So we are actually, we are doing what we'd say, we just want to extend the rule of law that says the same thing is going to happen. Well, if the same thing happens, this pattern must hold, there it goes. Of course, more abstract, it would look like this.
Yeah,
right? More abstract, you'd say you got 4 factors of A, 3 factors of A, 2 factors of A, 1 factor of A. Well, okay, don't put anything down.
Yeah.
But it's not 0. It's not that you're putting 0 down. It's that you aren't putting anything down. You have to. It's just like with slope, right? 0 slope and no slope are not the same thing. A slope of 0 is a number. Not having any slope, this line doesn't have any slope. But this line does have a slope. It's 0. So 0 isn't always none. What'd you do there? You divided by A. What'd you do there? You divided by A. What'd you do there? You divided by A. So what are you going to do there? Divide by stinking A. And you get 1. Sure. And then of course A to the negative 1, divide by A again. 1 over A. Now, kind of the cool thing here is that, yeah, that form works, but you can also use properties of exponents to prove this. Now, the one I think that probably makes the most sense to me is saying something like this. If I have a to the 4th over a to the 4th, you subtract the exponents, and that's how you get a to the 0. But a to the 4th over a to the 4th equals 1 because anything over itself equals 1. Right? I mean, as long, and we're really saying a can't be 0. I mean, I'm going to say that's given here, but a can't be 0 because 0 to the 0 is not 1. We don't know if it's 0. We don't know if it's 1, so it's indeterminate form. So we're just excluding that anyway right now in the conversation. But I'd say at least so a to the 0 then equals 1, and that's pretty good proof. Now, the pattern is probably more powerful until like an Algebra 2 class when the students are getting a little bit more. This is a good argument too, you could say that a to the m times a to the n we know is a to the m plus n. Okay, so we're going to use that formula there, right? So if I say a to the m, like let a to the n be 0. Well, that's clearly a to the m. Okay. So divide by a to the m, and I'll get a to the m over a to the m, or a to the 0 equals, now I'm going to use the same logic up here, and it's 1. And you can do actually the same thing with negative exponents, arguing very similarly. And again, remember this only works with a not equal to 0, but so maybe I should at least say that for 3. This is only when a doesn't equal 0, because then the best way to talk about that with high school students or secondary students is to say, well, 0 to 0 could be 1. Or 0 to 0 could be 0, depending on how you look at it, right? If you focus in on the exponent, then it's going to be 1. If you focus in on the base, 0 to anything is 0. So, which one is it? Well, I don't know. So we leave it as an indeterminate form, then you don't have to worry about that in calculus class, right? But maybe the last thing that I want to make sure we get is this is not a definition. Okay? Definitions, when I think about a definition in math class, you think of, I'm just going to describe the nature of it, and we're all going to agree that that's what it is. It's something that can't be proven, right? I mean, I can't prove. What's the definition of a quadratic equation? Okay, well, something's in the form x squared plus b. What if I wanted to call that thing a chalkboard equation? Freaking call it a chalkboard equation, and if everybody agrees that that's what it's called, it's just a term, right? So I'm defining something. If you want to call this a chair and this the desk, as long as everybody agrees, right? Why is this called a chair? I don't know. Okay. But this is not a definition. Like there are some definitions, like this right here. This is a definition. Square root of negative 1 equals I. Okay. We're going to define the square root of negative 1 to be a new kind of number, I. This is the definition. 0 factorial, 1. Why? Well, I mean, there's no common sense to it because 0 factorial. Well, you're supposed to, because think about this. With a factorial, you're supposed to start with a number and multiply successively less or consecutively less until you get to 1. 0 is already less than 1. The only reason we have to define it to be that way is because in formulas, sometimes it's in the denominator, right? And the formula to do what, 6 pick 6, something like that. Isn't the formula? The formula is n factorial over n minus r factorial. So if it's 6 pick 6, then 6 minus 6, you're going to get 0 factorial in the denominator. Well, but we already know the answer. Okay. Wait, did I say that right? Yeah. Yes. Order matters with permutations. So order matters with permutations. So that means that that means that there's 6 ways. Or not 6 ways. There's 6 factorial ways. 6, 5, 4, 3, 2, 1. Yeah, right. So there's 6 factorial ways. The only way to make this say 6 factorial is, and 6 is n, is to make this be 1. and 6 minus 6 is 0. 0 factorial. Okay, so make sure you go through those problems. It would be fun for me to hear you say, fumble through your words, and
Of course.
and try to make a couple coherent sentences. It'll also be fun to pull the ones out of a hat.
It's all right.
But I think that's,
all right.
but that is better than, it's certainly better than me reading all your responses afterwards.
Yeah, well, less work for you.
Better for
I like
you.
that.
It's less work for me.
That's all on video.
More pressure
Steve.
for us and less work
Oh
for you.
yeah, bring the camera.
No.
Oh, I'd actually like that.
Well, hey, you got it for
I
next
don't wanna listen to myself.
next year. You're gonna be well.